So, hello everyone. Good afternoon, good morning, good evening from wherever you are joining from different parts of the world. It is a wonderful thing to start with. We are the British Society for Geomorphology Postgraduate Forum, which is a postgraduate segment within the British Society for Geomorphology. And it's a wonderful time. Next week, we are having our conference at Leeds. And yeah, it's on the eve of the conference, we are starting this, and hope we will take this more forward with more speakers to come in coming months. And also, we are going to celebrate the ESPL's 50th anniversary this year, which is one of the celebrated journals of our society. And hopefully, we will have more updates coming up from the BSG on that. So we are a bunch of postgrads from different universities across UK and from different parts of Europe, and we have some recent people coming up from India as well. So we talk, discuss, try to do postgrad stuff, try to help support each other, and also try to find out career opportunities and stuff. So we had this idea long that we should start a webinar series based on different methods which we use in geomorphology these days. And so we came up with this idea called Geomorph Talks, Model Methods and More. And that here we are trying to understand different methods that we are using these days in geomorphology. And it's a wonderful opportunity to start with Professor Singhvi, who is a renowned scientist in this field. So thank you, Dr. Singhvi, for agreeing to deliver a lecture for us and starting off with Luminescence, and especially you whenever you have been established researcher in this field. So just give me a minute to introduce you. So Professor Singhvi completed his PhD in nuclear physics from IIT Kanpur in 1976 from India, and he has done his postdoc in from PRL, which is Physical Research Laboratory in Ahmedabad. So rest of his life, he has been working there, and he has been an outstanding scientist working on this. Yeah, he has been recipient of different fellowships like Ford Foundation, Oxford and St. Louis, A.V. Humboldt Fellow, and Heidelberg Leverhulme Fellow. Apart from them, he's also fellow of different Indian science academies, and also he has internationally acclaimed Luminescence dating laboratory in India, which he has been working so far. Presently, Dr. Singhvi is based at Shantou University in China, and he's working there as a scientist and as a senior scientist over there. So thank you, sir, for agreeing to our talk, and over to you, sir. You can go ahead with your presentation. Thank you.
Thank you, colleagues, for asking me to give the first talk. It's always a pleasure to interacting with younger colleagues, simply because it makes you feel younger. So thank you for giving me this opportunity. Before I start, as an old man, I'd like to give you a small advice, and I'll end up with a small advice. And that is that kindly value your work, evaluate every day how your work would inform either the conceptual space or translation space. And this has to be done every day, that how do I make a dent in the academic space that we have a page in the history of science whenever it's written. Now, with that said, I'd like to essentially share with you a very simple-minded introductory talk about luminescence dating. And it's about 5 decades that I started. And I'll try to share some of my own work I've done in India. And in these 5 decades, I have interacted with a lot of wonderful people, a lot of wonderful areas in the world, almost 50 to 60 countries. And I found that some of our work had a societal relevance. What we are going to talk about is crystals and their defects. We'll talk about what are the events we can date. We'll talk about the kind of synergies we need to develop and how can we make the world a better place in terms of planning. When I joined PRL, Ahmedabad, I did not know what is luminescence. I did not know geology. I came from nuclear physics. But over the years, 50 years, I spent now dealing with luminescence. And I thought I'd like to mention that this is the place I worked for 50 years. And they allowed me to build a small nest where I could build up a dark room and a lab, and I could work with wonderful people. So, okay, I like to show you some photographs so that you know who are the people who really made the technique as it is today. The very first photograph is of Professor Martin Aitken that you see here. He's essentially the father of luminescence dating. And interestingly, when he started, he had one student called Michael Tite, who eventually became the keeper of British Museum. And they thought one thesis will be enough to establish the method. And today, after a few hundred or a few thousand theses, we're still trying to learn and grapple with the technique. But he really established the method on a reasonably firm footing based on his physics. And we owe all our work to his hard work. Now, the next photograph you see nearby is David Huntley, who essentially showed that optically stimulated luminescence measurements are possible. And his seminal paper in 1985 was one of the wonderful contributions, and it has changed the subject totally. Van Weidel was at Denmark at the same time when Martin Aitken was doing. He was also trying to develop instruments for automated measurements. And today, all the systems that you see comes from his inspiration. And he did an enormous amount of calculations about radiation interaction with matter. I don't have a slide photograph of David Zimmerman, one of the early students of Martin Aitken, who essentially started the use of physics in luminescence dating. And he was the one who showed that factors like alpha efficiency, I'll come to it, are so important. And he established the fine grain technique. Anne Wintel may be known to many of you because she's still active. And she was the one who has really, with David Huntley, taken the field of optically stimulated luminescence with many others like Andrew Murray and others forward. The other people who I like to mention is Professor Lal, who was my director and the father of cosmogenic radioisotope dating, and Professor Walker, who is the father of fission track dating. And they got interested in what I was doing. And they went all out to help me wherever I needed. And there are many other wonderful people, many of you will know, but I don't have time to talk about them. I had a large number of students, and I thought I will express my gratitude to them by showing their slide first up front. As also, I like to tell you that our focus has been on trying to develop physics for new applications, and I will try to share that part of it. And I was variously funded by many universities and currently with Shantav University. Now, why is our work important? And you know that globally, there's an enormous pressure on the ecosystem, the human pressure, the ecosystem decline, climate surprises, and climate change. And there is a debate that will we remain in the glacial interglacial cycle domain, which we have been, or we may go to an altogether new state. And it's important, therefore, to find out what was the past extremes of climate that we experienced, and can we superimpose the global curve of temperature rise or carbon dioxide rise on this major climate cycle. The idea being that maybe we can find a paleo analog of the current situation in the past and then anticipate what could be the potential changes that may occur. Or we may conclude that we are entering into an altogether new state where we may have to find an altogether new equilibrium for the Earth system. So our work essentially helps provide a geological context of change in the past. Now, Earth is a self-organizing system at various spatial and temporal time scales, and things are happening on Earth from nanosecond scales to billions of a scale, and from atomic particles to continent sizes. And we end up with interesting patterns on Earth's surface, as we see in this case, in the case of dunes here, these are sand dunes in Arabia, or in meandering rivers or deltas, and you will find there's a pattern. The question, million-dollar question is how these patterns form and why they are actually resilient. And what are the time scales of their resilience? Because if you want to talk in terms of future Earth, you need to look at your land surface and see how it will respond to a climatic perturbation. And this has implications from food to hazards. For example, very recent floods in India have brought a lot of sediment flux from the Himalayas. Now, we do not know how much it will affect the productivity of the soils. And if only we had mechanisms to estimate the amount of flux which could be transported under such condition, the sediment could be transported, we'll have perhaps a handle on how to handle this catastrophe. Another area that is important is how the Earth will be under a purely abiotic conditions. Ecology will change. There will be regions of which will become abiotic, no vegetation, and how the river processes, how the dune processes will change is an important part of it. So that sets a context of our work. And one of the important things in this context would be that we essentially look at time scales of processes, what happens and when it happens, how long it stays. So there are three main important methods to date the deposit on the Earth. One is the radiocarbon, the second is the uranium series dating, and third is the cosmogenic isotope. Radiocarbon dating is 40,000 years. Precision of measurement is high, but when you do the calibration for a tree ring calibration, you essentially lose out a fair bit on the precision of the result. It works on organic matter with the assumption that organic matter is syn sedimentary to the sedimentary deposit. There are issues of diagenesis, contamination, reservoir ages, and more importantly, you have to assume that your sediment and the organic matter are at the same time, which is quite often not true. So you're looking at in situ organic versus derived organic matter. The second method is the uranium series method, where you look at the fractionation of uranium and thorium. Uranium is water soluble and thorium is particle reactive. So there is a kind of fractionation whenever is an aquatic system, and you can use that fractionation to be able to create a clock which can be measured using activities of uranium and thorium and their daughter products and get a time. The precision is high, but on the land, the samples like carbonates, which are very useful, which can be used for this kind of applications, very pure, rarely you find pure carbonates. So the applicability of this method is limited, and up to a few 100,000 years you can go, but very few samples would qualify for these applications of this method. An important method, cosmogenic isotopes, that I mentioned was developed at my institute at PRL, is a wonderful technique where you essentially look at exposure to minerals like quartz, feldspar, to cosmic rays, for which the technique would be useful. So often you need to apply some corrections for contaminations, and that compromises its applicability and utility. I also talked about the cosmogenic isotopes, which is a wonderful new techniques which requires measurement of atoms produced by cosmic interaction with minerals like quartz and feldspar, olivine, and then you can count the atoms and tell with the cosmic flux estimation, tell how long the material has been exposed. This is fine for rocks which are remained in situ, but
please wait for a few more minutes. Sir is changing the system and he will be online soon.
Am I online now or not? Am I online?
Yes, you are online, sir. Everything is fine from your end.
Can you hear me? Can I continue, Joyesh?
Yes, sir, you can continue, please. Go ahead.
Okay. So, and the measurements can take you to a few million years in time to a few thousand years. Below that is not possible because of the fact that the measurement concentrations of very low measurements are not possible. In the case of sediments, where the material is transported, there is an issue of how much of the cosmogenic concentration, isotope concentration was inherited and how much was gained subsequent to deposition at sediment. There are ways to handle this, but in a way it gives you an interesting way of analyzing a sediment profile. As I said, it is important now to realize that not one technique would work, but many techniques on the same sediment are essentials to understand the sediment dynamics. Luminescence was born in 1970, and then in 1985, David Huntley showed that he could measure optically instrumented luminescence by stimulating a sample with a green light and measuring in the ultraviolet light. The important part of luminescence is that you essentially look at the age of a sediment when it was deposited or when it was formed. It needs no calibration or standards. In fact, one of the questions against luminescence dating has been that we don't have standards. But what people forget is that we have internal standards of calibration, and that allows us to build up a self-consistent story. And we do not need any external standards. Typical precision is about 10%, but if you are hardworking and if you can do a large number of replicate measurements, you can hopefully, at best, in some good cases, come down to 5%. Below that is not easy to get. An important part is that in a mineral, we have many aspects which can be dated. So you can have a multiple phases within a sample which can be dated. For example, you could date sands, you could date individual grains, you can date gypsum in the matrix, you can date volcanic ash, carbonates. So each one of them can be dated, and you can build within a sequence a self-consistent story. That is not possible with any other technique. The age range is continuous from 10 years to about 500,000 years, some cases a million years time scale. And it's important because 10 years to about 150 years, we have instrumental records. And therefore, this method would allow you to calibrate all your data and then extrapolate backwards to with more confidence than you will do otherwise. So calibration of proxy with time is possible with this technique. However, it is not a routine method, and because the mineral luminescence is extremely complex and extremely sensitive. So you have to be careful in handling materials. Each sample has its own story to tell. But it's a fun to hold a sand grain in your hand and tell all about it by simple laboratory measurements. If you look at the technique, this was a comparison we did about a few years ago, and it will show that from about 10 years to about a few 100,000 years, we are able to batch with whatever standard controls were available. And I recommend that you look at this article led by Andrew Murray for more information. But we believe that we have more than established the method for routine uses. This method has not only found use in application to earth sciences and archaeology, but has also found major use thanks to the development in earth sciences in radiation dosimetry, cancer therapy, in retrospective measurement of dose after nuclear accidents, optical data storage, and there could be another talk on these issues. In case of sediment, wherever you have quartz or feldspar, you can apply this method. Could be a large number of sediments, fluvial to Aeolian to lacustrine to glacial deposits, archaeology, mineral properties of sediments, and various rocks and their exhibition rates. So this is a fantastic review by Mehan and then Eddie Rhodes in Annual and Reviews of Earth Sciences. I recommend that you look at it. Additionally, as I mentioned, you could also have nuclear accident, radiated foods. All the food irradiation occurs for safety of food, and we can continue. We can use these techniques, OSL techniques, to very quickly measure whether the food is safe to consume or not. And OSL is used routinely nowadays for such measurements. Cancer therapy, we can do a very precise cancer therapy thanks to OSL, because we can measure incremental dose at every millisecond or every second and stop exactly at the point you need to stop in terms of the dose being delivered to the tissue. That's another. And of course, authenticity of art objects is another issue, that where no other technique can match luminescence, because you cannot fool a luminescence test, and I will tell you why. So, are you hearing me?
Yes, we can hear you, sir.
Okay. The other applications I mentioned was the health physics, where we use OSL for dosimetry of the radiation workers on a routine basis. Radiation therapy I've talked about. Space dosimetry, when the astronauts will go in the space, the kind of radiation exposure they will give is measured by luminescence. Nuclear accident dosimetry I mentioned. Hiroshima, Nagasaki, Chernobyl, and overbound nuclear testing in America, all were revised based on the studies done using luminescence, led largely by Ed Haskell in America, and then Ian Bailiff in England, and Juan Maydal and other group in Rizzo. They did a wonderful work in reassessment of the radiation dose using porcelain, using building bricks, and I will talk about it in a bit more detail. In meteorites and space sciences, we can look at the TL and the thermal and radiation history of meteorites. We can talk about the orbit of the meteorites, how close a meteorite went to the sun, because once it goes nearer to the sun, more than one astronomical unit as Earth, the temperature will be higher, and its luminescence will be appropriately erased. So with very simple calculations, you can establish the orbit of a meteorite prior to capture. Classification of meteorites is now being done routinely using TL sensitivity, just because the TL sensitivity is very sensitive to the crystalline order, which in turn is sensitive to the metamorphic history. And so it's very routinely being done and earlier meteorites were classified at class 3, 4, 5, 6. Now we talk in terms of 3.1, 3.2, 3.3, 3, and on and so on. And we can also date the terrestrial age of meteorite based on the fact that it forms a fusion crust when it falls due to heating. And then any luminescence acquired by the crust on its stay on the surface of Earth can be dated like any other heated object. Quite a bit of work was done by the groups in St. Louis on moon rocks, and they used it to be able to find out the cosmic ray fluxes through time and what was the mixing rates of the lunar regoliths. And on-site work on Mars is being planned now, where we'll find ages of the sediment on Mars, and the groups at Rizzo and in Oklahoma have developed small instruments that will go on a spaceship and make the measurements on board. This instrument, which is seen in the photograph, was developed by one of our students, Mayank Jain, and his team at Rizzo, and weighs only 600 grams or 700 grams. And it will do all the measurements of sample and be able to give you an estimate of age based on it. So it shows you the kind of range of things we can do with OSL and TL. So essentially, if you have a hammer, everything is a nail. So if you have TL, everything in geology is tractable. And I believe I can easily say that it's a geological hammer for the quaternary, because the 70% of the work on quaternary chronology comes from OSL and TL now. In the Indian context, we have about 13 labs, and we have essentially been able to map the Indian surface reasonably well. Of course, there's no end to the work, but first order story of the Indian surface is now known, and all the groups, and the number is about 13 now, and about 500 publications have come from India, 50 theses have come, and about $150 million has been spent on these labs. I have summarized in an article which is here. Now I'll talk about luminescence, and then I'll talk about luminescence dating. Luminescence is a process by which an excited material emits light over and above the black body radiation. So this important part is the black body radiation is when you heat a sample to red hot, it becomes red hot and pure, but they start emitting light even at 300 to 200 degrees centigrade, which we cannot see, but sensitive photomultiplier you can see. So anything above that, which is induced by radiation, is luminescence of interest to us. If you look at a pottery sample under a cathodoluminescence excitation, you will see some bright spots. And these are the bright spots, which are essentially quartz or feldspar minerals. This is the X-ray, dispersive X-ray analysis of those. And this we found was essentially quartz and feldspar. So most of the signals that we get from sediments are from quartz and feldspar because they are extremely sensitive. What happens is that when you expose a material to radiation, a mineral to radiation, like alpha ray, beta ray, gamma ray, you essentially create ionization. Now this ionization essentially creates free electrons and free holes, which walk in the crystal, and some of them get trapped in a defect in the crystal. A defect is a place you need a charged environment which can hold an electron for some time, maybe a second, maybe millions of years. And as you increase the radiation, the number of electron hole pairs produced are increased, and the number of trapped charges increases. So as the time goes on, more the radiation, more is the ionization, more is the trapped charge. Now, when you stimulate the material in the laboratory with heat or light, you physically evict these electrons, and then they come back and de-excite and give you light. And this light is proportional to the radiation exposure, and we exploit these for our studies. Now, all crystals are like human beings, and the brightest human being is the most eccentric one, has the most defects, and is the most complex. So whenever you have a bright signal, you have to be careful that you have a very complex system to deal with. Just to give you a feel of the whole thing, that 1 ppm of impurity would give rise to about 10 to the power 17 defect states. And how they interact with each other, how they talk to each other, how they manipulate each other is the subject of studies. And what we get is the end product of this luminescence. And the most of the work that we do essentially is focused on understanding how to make sense of this luminescence, not violating any of the physical laws that we understand today. So the most of the research effort in luminescence today is what is the nature of defects, how the electrons move around the crystal, can we create new defects or kill some defects, and we use almost all possible spectroscopic methods to analyze it. And like human beings, each mineral grain has its own story to tell. So you cannot generalize any mineral specifically for any other application. You have to create a calibration curve, create an analysis of each mineral for each time, for each situation. And that makes it more complex and not a routine method. In terms of physics, we have the valence band with all the occupied states in a crystal, and we have conduction band, which is no charges there. And we are looking at semiconductors, so large band gap materials. And when we analyze, essentially I take an electron from here and put it here, which is walks in the crystal and gets trapped at a metastable state. These are the defects in the crystal. And then when you excite by heat or light, they come and recombine and give you light. The stability could be from a few seconds to a few millions of years. And if you keep on exposing, then there will be a time when you cannot create any more defects because there are no more traps to do so. So typically we find that for quartz, the saturation occurs around 200 degrees. That translates to about 200,000 years as a dating limit. And for feldspar, it is about 1,000 grays, so translate about few 100,000 years. So that's why we are looking at feldspar more intensely nowadays to be able to get to a million-year regime. And there's a lot of things can be done with this mineral. So whenever there's a complexity, there are also opportunities, and that's what I'll talk about now. Now, if you heat a sample at a constant rate, you will get a curve like this, which is called as a glow curve, and this is called as thermoluminescence. If you excite a sample, same sample with a green light, you can measure in the UV blue, you will get a curve like this. And this curve has the same kind of information as this curve has. And we need to understand these curves and their behavior to be able to. Now we call them as optical decay or shine down curve. And mostly quartz and feldspar and some other metals are now being investigated. We could also use infrared light, and this was the work of Galina Hood, who excited with infrared light, very small energy, and was able to see a signal in the feldspar. And she was able to explain the reason, physics reason. But again, what we get is the shine down curve or optical decay curve. And from this, we need to build up our story and understand how and what is the message these signals carry. Interestingly, you can either do a constant stimulation or a pulse stimulation, and we use these to our advantage to isolate various signals. So we do time resolved measurements, we do pulse measurements. We use variety of stimulation energy, green, blue, violet, and we use variety of spectral windows to be able to get the optimum signal which will meet our requirements of dating applications. So we have multiplicity of signals, and this means we can use in the same example varied signals to get a self-consistent framework. Now, for estimation of age, the simplest way to understand age is to look at a beaker being filled by a drop rate of water. So I'm filling a beaker with a constant drop rate and seeing, so if I want to know what the time taken for the beaker to be filled up, I need to ensure that initially the beaker was empty. I need to know, I can find a way to measure the volume in the beaker. I need to have a drop rate which is constant. And I need to ensure that there were no unknown inputs or outputs from the beaker during the measurement and its time in this period. So this is a closed system assumption. Now, if you have a TL, then your beaker is being filled. You have a mineral which is after a certain zeroing event. It's being filled by radiation at a constant rate. So with the time, your signal will increase. Whereas if you have a leaky beaker, you start with the filled beaker and the water leaks at a certain drop rate and the signal decays, as is the case of radiocarbon. Again, in the radiocarbon, you have to know that the leaks that you know are the only leaks, which is the radioactive decay. All otherwise, there could be other contaminating issues will come in. So this beaker essentially allows you to conceptualize and visualize all dating methods, irrespective of where you want to apply. The assumptions in all methods are that we can measure the initial value and the final value with accuracy and precision. we know that drop rate or the leak rate is constant. And there's a mineral has remained a closed system. That means there were no unknown leaks or inputs during the time we are looking at. Now I'll talk about zeroing, drop rate, phase dose, and stability in the next few slides. So you have a mineral in the environment, and you are essentially exposing it to radiation field arising from the decay of uranium, thorium, and potassium, and they are bombarding the mineral in a variety of manner. Alpha particle have a small range, so only the skin is irradiated, whereas the beta and gamma ray will go through the crystal. This has own implications, and that will be seen later on. Now, which is the most important part which we use TL and OSL for, is to date sediments. And they rely on the fact that sediments, when exposed to light, lose their luminescence very quickly. And in the case of OSL, in a few seconds, you lose all the signal. So while it allows you to make sure that the sediments are zeroed very quickly, it also ensures that you have to be careful in the laboratory that you do not expose the sample to any unknown exposure. And I recall an accident we had in the laboratory, that one of my young students had a young girlfriend, and while making samples, he was talking to his girlfriend, not realizing that while he was talking to his girlfriend, he was bleaching the sample through the light of the cell phone. And it took us about 6 months to realize what was wrong, because we did not get any signal on the samples he processed. So kindly be careful when you talk to your spouses or friends when you are in the lab. The events that you date using luminescence are where the initial luminescence is reset to 0. So you have a mineral formation event like gypsum or slags, speleothem, where the mineral forms here. So you start acquiring crystal, you have a crystal structure here, and there onwards you starting measurement, increasing luminescence. Heating is up to 400 degrees, such as firing of the pottery or ceramics, fireplaces, you can date them, the last heating events. Bleaching, I talked about the most recent transport event. And in earthquake, you can talk about the most recent frictional heating of fault gauge formation. And one of the examples that I will show you is of viscous heating in case of sand dikes. More recently, the RISO group has excelled in developing methods to date surfaces. And the idea is that the surface, when it's exposed to sunlight, the bleaching front goes inwards as the sunlight progresses, because the flux of light here will be much less than flux of light here, and the D'Alembert's law follows that. So the bleaching front will keep on progressing inside. So if you make a measurement of sample with depth, depending on where the profile comes, you can get an estimate of the age. And that is a very interesting new work coming out of RISO and many other groups now. An important part in the case of sediment is to remember one thing, that amount of sunlight seen by sediment, though it's few seconds of sunlight, but is available. And important is that the flux, the spectrum of daylight can change due to a variety of factors: turbidity, sediment load, gleying, duration, and transport velocity. So these things change the amount of sunlight and net bleaching seen by the sample. And I've given you an example here that if you look at the spectrum of sun and the daylight in the air, and same underwater about a meter or two, you find that both the high energy and the low energy part are gone. So you have to deal with this kind of spectrum, and this has to be folded in the analysis to understand what is happening. Now, think of this figure with this figure, where Spooner has shown that the bleaching efficiency goes down rapidly with the decreasing energy. So if you have this, then perhaps you will be here. If you have this, perhaps you are here, 10 down, hold down, slower rate of bleaching. So we need to understand the sedimentary context in which the material has been transported, the amount of sunlight you would have seen, and do all possible field measurements to make sure that we understand what the sample has gone through. One of the simpler ways that we often follow is to analyze a sample which is recent sample, transport it hopefully under similar conditions, and use that as a benchmark work to be able to extrapolate back in the future, back in the past. The drop rate I talked about comes from uranium, thorium, and potassium, some bit with cosmic rays, and then their decay products. Now, we often assume, and quite often reasonably so, that these series are in equilibrium. But there are situations, especially where water is involved, that you can have uranium without the daughters or a thorium without the daughters. And we need to work backwards. But these procedures are known. And once you know the whole chain, you can compute the dose rate very precisely and calculate the age. So this is something we can handle with a reasonable confidence and essentially make sure that we get the right age. Assuming equilibrium, and this potential case of disequilibrium would be suicidal. And insulation against this comes from potassium, which gives you a fair amount of dose in the case of coarse grain. So this has no such issues of fractionation. And we often look at potassium and then make an assessment of what could be the effect of potential changes in these chains due to potassium being there. Nature is complex. To realize and to give you a feel of the complexity, you can think of all kinds of minerals, all kinds of mineral types, all kinds of grain sizes are in a grain. Now, we also know that in the nature we get alpha particles, beta rays, and gamma rays, which have varied ranges. So depending on where an alpha particle is emitted or beta particle is emitted and what's the neighboring grain size, the whole scenario looks very complex. And therefore, we have to make a simplifying assumptions so that we talk in terms of the heterogeneity, and we know how to cope up with heterogeneity of periodose, heterogeneity of dose rate, and time dependence of dose rate. We now deal with specific grain sizes within which hopefully is nearer to the mean grain size of the sediment, and then analyze and then do all the calculations based on that grain sizes. I'll give you another example. For example, we can normally we work with 4 to 11 microns for fine grain, which was developed by Zimmerman, and the coarse grain was first pioneer was Stuart Fleming. And fine grains, we assume that they get full complement of the alpha dose because alpha dose range is 20 microns or more. Coarse grain, we remove the outer skin of 20 microns and say they did not get any alpha dose. So this is a laboratory simplification that we do to realize the nature in the lab. And quite a bit of calculations have been done to do this. Now, for example, in the case of single grain, we ended up with the situation, we got a large scatter of grain, which should not have been the case because samples were from deserts. And we realized that the scatter comes from the fact that the potassium in a soil comes from a few grains of potassium feldspar, which have 14%. So you have in a matrix hotspots of 14% potassium emitting beta particle. And depending on a quartz grain being near to it or away from it, will have a smaller or higher complement of dose rate. So same sample, if the potassium is 0.5%, you will get an effect like this. Potassium 3%, you get more averaging done. So the amount of potassium will essentially tell you what is the heterogeneity in the beta dose distribution that we need to take into account. And this is the work of Murthy, who has done a great, and he has given an equation on this. The measurement is simple because you essentially shine a sample with a laser or a LED now, and then put it on a grain or a sample and measure it. And then you do a various calibration. I will not have the time to go into SAR protocol, but essentially we do is we make a measurement of the sample as received, and then use the same sample to create a calibration curve with radiation dose and read the sample intensity on it. I will like to remind you about the work of Lars Botter Jensen, who really pioneered the automated measurements in luminescence dating. And today we are able to apply luminescence successfully is largely due to his 5 or 7 decades of hard work and his group's hard work to do that. So this one man persistently refined automated measurements, which we think we take it for granted today. We do lots of measurements, and then we do a fair amount of statistics on the data to be able to get a meaningful estimate. And I would recommend the work of Galbraith here to be able to analyze, where he has given various statistical technique to do that. For example, if the aeolian sediment well behaved, you will get a single valued function, whereas fluvial sample would have a larger range of equivalent doses, simply because they may have seen varied amount of sun exposure, and they may have a smaller amount of residuals. So we know how to handle those kind of data, just to give you a feel of the data that what happens. Now I'll come to my own work on deserts, and I'll picked up a few examples where some societal impact was or conceptual advance was involved. One of the work was on the deserts, which have minimum biogenic inference. It's a direct interplay of geology and climate, and it impacts the climate via albedo changes. And I'll tell you what is important in there. And 50% of the land area between north and south is desertic. So the questions we were seeking to understand is that expansion or contraction of desert, was it synchronous or asynchronous, which will in turn imply on albedo changes. Hydrological changes, were they synchronous or asynchronous? Correspondence between the sea surface temperature and desertification, and response time of different desert sea. And the groups at Oxford, especially led by Dave Thomas and Link Lancaster in America, they have done a great job in taking this field further. Mark Bateman, many others. We were fortunate that we were the first to be able to show that we can date desert sands. This was way back in 1982. An important aspect of this work was that till this work and this applications of luminescent dating, it was assumed, and this is a paper in 1994, that the world desert expanded and contracted simultaneously. That means the world albedo changes were occurred simultaneously. This is the large land area. When we applied these techniques, luminescence dating to dune records, we found that we got a large scatter, and very rarely there was alignment at the last glacial maximum, which was the case. And we then were able to understand that this is to be expected in any terrestrial environment. So correlation was an issue that we addressed too. Of course, anyway, before I come to that, I'll just say that now we have a dunes atlas that has been created, and all the data on the dunes luminescence ages are available. So you can look at the global deserts at any instance of time that you like to see. And this being updated. Now, an important outcome of our work on the dunes and deserts was that we found there were large breaks in the record, be it lowest, be it desert scene. We found that we never found a single record which was continuous. And this was explained elegantly. We had done it, but more elegantly by Kosurek. He said, you have a climate, you need to have a sediment production, sediment be available to transport capacity, and then what we see is a preserved record. So by definition, a terrestrial sediment is a preservation record and not a creation record. And therefore, it will be only, the preservation will occur only when there is a transitional climate. And therefore, many people who used to correlate any of the strata with marine isotope storage or with ice core records are flawed simply because we are looking at two very different systems. One is a preservation record that occurs only for a 10 or 20% of the time. Other is a continuously accumulating record. So my submission was that with luminescence, which shows the large gaps. In fact, there's a good book by Ager. We say that this sedimentary record on the land is like a mesh with a few things, all voids and a few things hanging by thread, something of that sort. So I think we need to be careful in correlating any land record with the ice core records. Where is the causality? What is it that happens on the land that is informed of a teleconnection far back in Antarctica? Otherwise, you are comparing X with oranges. Another interesting thing we could do with the help of Nick Lancaster and Gary Koselleck was that in the Western Africa and Mauritania, we were able to look at the dune trends and remote sensing, and three major trends were found out: northeast, southwest, northeast, southwest, and then north-south. And we were able to locate in the field in these dune areas, sample them, and we were able to reconstruct the paleo winds through time for the last 25,000 years. We have done a similar story in Arabia, where we have been able to create a record of paleo winds for the last few 100,000 years. So this is an application that you can now use this data to see how the wind regimes have changed in the past. The next is the fulgurites, which are the materials produced by the strike of lightning, where lots of energy is being deposited and temperatures up to 30,000 degree Kelvin can be raised. Now, when this happens, the material where it strikes melts and captures all around it and kind of keeps it safe for a long time. It's a glass now. It looks like this glass looks like a root-like structure. Now, we found a fulgurite in Libya where last 100 years data shows no lightning strike occurred. So in this fulgurites, we were able to develop this method and date these fulgurites because it has got some quartz which were heated, and we could pick, and they were just captured without melting. So we could take a few quartz grains after this and date them. And we found that this fulgurite in Arabia, in Libya, was formed around 15,000 years ago. That means now, interestingly, we also could find out in this fulgurite traces of microliters of gases, which were analyzed in Mexico by a colleague, Gonsalves, and he found that this essentially would have formed in the organic matter content of 0.1%. Now, organic matter 0.1% exists at the Sahara-Sahel boundary here nowadays. That means that in the past, the Sahara-Sahel boundary was up north, about 1,000 kilometers north. And that is the way one can now construct paleoecology using fulgurites. And a major program by the Germans is underway in Sahara, where they're looking at every single fulgurite they can lay hands on to do paleoecology. In Tibet, we were able to date the frost wedges, and from that, because of sediment infill and outside, and this was one of my hosts here, Zhongping Lai was involved as a student, and Stephen Porter, and we were able to ascertain that this frost wedge was formed around 15,000 years based on the sediment dating here and outside. And interestingly, frost wedges formed with the air temperature of -8 degrees centigrade. So at 15,000 years ago, we said the air temperature was -8 degrees compared to the present, which is about -4 degrees average air temperature. So right now they don't form frost wedges, but in the past. So we essentially were able to use luminescence to constrain past temperature changes using an appropriate sedimentary record. And this has been subsequently confirmed by modeling studies as well. Another interesting thing happened was in India, 1970, there was a major flood, as has happened recently in the Ganges. And there was a lot of hue and cry that this is because of deforestation in the lower Himalayas, that the sediment was let loose, and it was the one that was transported. A huge sediment pile of 10 meters was created downstream. We then analyzed the paleo flood record of this region, and we did also the sediment provenancing using strontium and neodymium isotopes. And what we found was that in 1975, the higher Himalayan sediment flux was about higher, and lower was still higher. And this normally it was higher was always high, and the lower was low. But in 800 years ago, also there's similar situation occurred. That means glacial lake outburst every few hundred years will occur and cause such floods. Deforestation was a cause, but not the only cause. So here we were able to resolve that geology will always play a part, irrespective of human interventions. And now what has happened is that human interventions have increased the glacial melting. So there'll be more of GLOF kind of events. But here, every few hundred years, you are going to get a GLOF event. That is what this work showed. Important thing was, and interesting, that in the USA, there was a large number of legal suits on the state and that people got sickness due to radiation exposure due to organ nuclear explosion in the 50s and 60s. And the state then commissioned a study, and one of the person called Ed Haskell came with the bright idea that he will analyze the building bricks which were built after the World War II and at the time when the nuclear testing was going on. And so he took building bricks with a known age of plus minus 6 months, took the bricks, found the age. And what his argument was that I can compute the age expected of a grain in a brick in the last 30 or 50 years. Anything excess would be attributable to radiation exposure from fallout. And he was able to compute a large number of such bricks and was able to show that the fallout was not as much as people had intended to. So all those legal suits probably fell apart because of this work. And this was a kind of an application of luminescence dating that was important. Now, new physics, I'll take another 5 or 7 minutes, I'm sorry. But I will try to tell you how geology has helped physics. And of the three, I'll take 2 examples of alpha efficiency and athermal fading. And these have historical importance. As I showed you that the age equation is essentially contribution from alpha particles, beta rays, gamma rays, and cosmic rays. In the 1970s and pre-70s, Elizabeth Ralph and Mark Hahn were very well-known radiocarbon dating people at the Philadelphia Museum. And they applied this method and they computed the age based on that all the alpha particles, beta rays, gamma rays, and they were computed, gave the similar kind of results. So they got an ages which are underestimated. And the whole method went into disrepute in America that nobody would like to do TL or talk about TL at that time. Till Zimmerman found that alpha particle efficiency in TL production is much lower than beta, gamma ray, and so. And the argument was simple that if you take an electron in a matrix, it is weakly ionizing, so it will keep on producing electron hole pairs continuously along the track. And therefore, at any point of time, there will be sufficient number of traps available per volume to be able to absorb this. So their efficiency is higher. Whereas alpha particle, being a heavy particle, puts all the energy in a few microns. So although they have ionized the crystal, although they have put in the energy, the crystal does not have the capacity to absorb all those traps, and most of them are wasted. And the efficiency of alpha particle is about 3 to 4% in absorbing signal. So the same energy, you find an electron is more efficient in producing luminescence compared to an alpha particle. This opens up a new field of how high energy charged particle interact with matter. But for us, it was important to realize that this alpha dose, which was taken as 100% here, becomes 3% here, and the ages all fall back in time. Now, this small error essentially implied that in the USA for 20 years, there was no funding for luminescence dating. And then when they were sure that method is working, they got back, and now, of course, it's a flourishing subject in America. The second work, which was done by Ann Wintel and Visosikas, and then finally Mike Jain, was that normally we find that we have, showed you a picture, we have a trap and electron trap and a hole trap. Now, normally they don't talk to each other directly. They can only talk to each other when you excite the electron and goes to conduction and meets here. But in feldspar, what we found that these fellows used to talk to the quantum mechanically. So there was the chance that it can leak out without going through the normal excitation process. Initially, Wintel was not able to understand. She called it anomalous fading. Now we call it athermal because it's a quantum mechanical leakage. And this implies that you lose signal without knowing. And so it calls for corrections. And we do that corrections based on laboratory measurement. Though the million-dollar question still remains, how a few days of laboratory measurement can be scaled up to geological time. Now, one of my students is now doing a kind of inverse modeling, and we believe that there are some of the apprehensions may be correct. I will hold on till my student finishes the work, but we have some very interesting new results on the athermal fading that are coming up soon. I would like to end here with a small advice. I mean, I have tried to give you a flavor of how the method works in the 40 minutes I had, plus 10 minutes of my disruption. I'd like to give you a few things which I thought I will. Firstly, to be able to succeed in life, you need two things: ignorance and confidence. And it was true in my case. I was ignorant about geology, I was ignorant about archaeology, I was ignorant about luminescence. But I was confident that I could do nuclear physics experiments and I can build instruments. So I jumped in and I thought it was a great fun then. So many turmoils, many hard parts, but it worked out well. The second thing is, it was your own conviction about the work you do is important. When in the 70s, the work of Ralph and Hahn essentially showed that method has not worked well and people gave out on, Martin Aitken persisted with it. And it took him 10 or 15 years and many theses of Mike Tite, Ralph, Hahn, Bailiff, Murray, Wintel, all of them, each one sorted out a problem till they got to a stage the method started being appreciated. So you may not get an audience to start with, but if you are convinced about your work, then the audience will automatically gather in time. The third thing is that failure is a key to new discoveries. You may plan a smooth ride to your thesis, but this will never happen. You will get pitfalls, potholes all through. And remember one thing, failures are the ones which prepare you for success, and outliers are the ones which will give you outstanding scientists. So never ignore an outlier. Never say outliers, I'll forget about them. Follow the reason for outliers, and I can tell you, you will get outstanding science. And in fact, whenever we got an odd results in the lab, my students were unhappy and I was the most happy person, because here was a case where some new thing is waiting to be discovered, and we did that. It took us time. So the world out there would be sure to take your notice of your work, provided you are consistent and at it all the time. I wish you all the best for all the young colleagues. I'm sorry for the break in between, but it was beyond my control and competence. Thank you so much.
Thank you so much, Dr. Singhvi, for such a wonderful talk. Yes, debarring all the issues that we had, but finally we managed to complete. So the floor is open for any questions. I would suggest couple of quick questions if we can have. So if you can unmute yourself and ask a few questions to Dr. Singhvi.
Hello? Hello?
Hello.
Yeah. Can you hear me?
Yes, we can. Yes, we can hear you.
Okay then.
Yes. So we have sir, we have a question on the chat box. So it says, how do TL and OSL differ in their sensitivity to environmental radiation doses, and how does this affect age estimates? It's from Ujjwal.
I think they are the same thing, and they are ideally TL is more sensitive because it has got defects, more defects included, which are both light sensitive and light insensitive. So TL will give you more light. It's a question of what applications you are looking at. OSL has its own advantages, TL has its own advantages. And accuracies wise, I don't think there'll be much to take away from it, because 50% of the dose comes from error comes from the environmental dose rate, which is common. Measurement precision in OSL and TL may be slightly variable. OSL with the ease of measurement can do more measurement, but I don't think you will get too much of a difference between the two. Maybe 7% versus 8% or 10% error. That's all. But in terms of the results, they are comparable signals, so they should give you the same result. And we have in our paper shown in Quaternary Science Reviews in 2000 that we got similar results with TL, with OSL, with infrared simulated luminescence. In the case of a dune sequence in Thar Desert, we got similar results throughout. So there was a consistency in all of them.
Yes. Yeah. And then we have a very basic question, which I think you can easily answer, is what is meant by dose rate and how do you calculate that? So it's from a young scholar, Dakshina.
Yeah, what happens is that you have an environment, any rock, any soil, any room you sit, you are exposed to radiation. And this comes from small amounts of uranium, parts per million, milligram per kilogram, thorium milligram per kilogram, and potassium percent. Now these fellows keep on emitting alpha, beta, gamma rays depending on their half-life, which is about a few billion years, 4 billion years, 3-4 billion years. So you can assume that they are constantly emitting light and your radiation flux is constant. And from there, so you know that if you annually, you can compute, and there are tables available, they'll tell you what is the amount of radiation flux coming out of these fellows. So you measure the amount of radioactivity, and then you measure where the radioactivity is located, what is the sediment type, what is the grain size you're looking at. There are standard procedures to be able to calculate the dose rate. And we use hyperpure germanium systems to measure the radioactivity and their activity levels of various daughter members of uranium and thorium. There are other techniques like mu dose and others have come into the market which are quicker, but you need to be very careful about the geometry factors of your sample. What is the radiation field, and then calculate. It's not trivial, but it is doable.
Yes. Yes. So yeah, there is another from Dr. Priyank Patel. He asks, how accurate are field-based luminescence estimates using POSL readers compared to lab-based?
Yeah. See, there are many issues in field-based radiation dosimetry. It's a good tool for non-geologists to look for breaks in the sedimentary records, right? But there are issues of like glaying happens. Now you measure it, you will not be able to understand the glaying, was it in situ or outside. So I would take it as a ballpark measurement still. I will not be comfortable in accepting them as a real number.
Yes.
That's how my take is, because there are so many things happening. You can't have a very fast buck in this. I think you have to go through the rigor to be confident of what you're saying. Yes, in the field, if you want a gross break of 2,000 years versus 10,000 years, yes, go ahead and do it. But a discerning eye, a field geologist will automatically look at the soil automatically forming there. So I'll be more comfortable in looking at the three-dimensional exposure in the field, and then have a soil scientist working with me rather than looking for instrument to break. It's good tool, good fun, but it has to be used with great caution. There are many things
Yes.
happen in the field which we don't know. Dose rate is another issue that you will have to be worried about. So,
Yes, I think the POSL is a good range finder for us, but yeah, we can't rely.
So as
Yes.
long as you are comfortable in saying that is a rangefinder, I have no problems. But
Yes, yes.
please don't go
I think we can't rely. Yes,
please
we can't rely ages on that.
don't be too enthusiastic.
Yes.
It is
Okay,
extremely
so
seductive. It is extremely seductive, but don't go after it.
yes, it's a small tool, and you can just carry it and yeah, get some edges or some like ranges, as we say, and we can see some curves out of that, shine down curves. But yes, yeah, we shouldn't be convinced about that, because it's not you are not going through the hard process, like from
See,
the wet chemistry till end of in the reso.
I have a
So
saying that whenever the measurement is easy, there's something wrong somewhere. Number one. So, and
yes.
whenever the quartz is dull, the student has to be bright to make sense out of it.
Yes. Yes. So yes, I think we have these questions. If you have something more, okay. So yeah, we have Pankaj Kumar. Dr. Kumar says, okay, so are you a physics person by study and have contributed a lot in earth sciences? How were your initial days about learning earth science terminologies? And how did you take criticism, if any, by others about your knowledge of earth
Yes,
science?
that's a good question. Firstly, physics, learning geology was very complicated. I used to write equation like Pleistocene is equal to Holocene plus, or the quaternary. I did all those things. It was a tough learning, and geologists were very tough customers to deal with. But slowly, I learned it. I took every criticism very positively. And I think that was the one which allowed me. Every criticism essentially led to a doctoral thesis. And every anomalous observation led to a doctoral thesis. So I think your critics are best friends, because they, through their criticism, allow you to look at the alternatives that may be available. So I valued all criticism positively. I never took it as a negative thing, and which is probably what helped me grow in the field.
Yes,
I always was happy when there was an outlier. I was the most happy person in the lab. When the students were unhappy, I was happy, because the outlier is trying to tell you some new physics. Can we understand
yes.
it? So that was my enthusiasm.
It's like when we were kids, we used to, if we were doing maths, and if we had some values which were not matching the answer in the back side of the maths book, so we were always confused. Oh, we have gone something wrong. So I think that thing continues till our
Yeah,
later
I think
ages. And
we should
yes,
look for a reason for outlier is trying to tell you something. It's shouting, but you have to understand it. So I
yes,
said
yes,
in the slide, I say celebrate failures and outliers.
yes. And sir, the last question is again from Dakshina. She asks, what is an average standard depth of sediment sample collection to go with OSL dating? So
Any depth is fine. I don't think because as long as you know the depth, we'll do the calculations. So that's not a problem. On the surface to the base, not a problem at all. Because you see the range of the maximum signal in coarse grain comes from potassium. The range is 2 millimeters. So worst case, I will lose half the dose if you're just on the surface. But I'll know, as long as I know where the sample comes from, we can handle it. I don't think there's any requirement of any depth. Have I
okay,
answered
so
that?
yes, I think so. Yeah, that's quite. Thank you. So yeah, so I think that's a lot of questions we have already answered. If you have further queries, you can email Dr. Singhvi. I think he would be happy to. Answer you. So it's time to say thank you to everyone. So I would like to thank a couple of people. So firstly, Mr. Shashi Shekhar Shukla from JNU. So he's been phenomenal support for me for organizing this, and also Mr. Ayapadas from Oxford. He's working with Julie Durkin. So he and both of them has been a phenomenal support to organize this webinar, and you would be seeing more webinars coming up in a couple of months after this. Also want to thank other people who were also here, some famous names like Dr. Pankaj Kumar, then Dr. Devendra Kumar, Helen Roberts, thank you for coming in, and Professor Stephen Tooth. So thank you everyone for joining this webinar.
Is Dr. Helen Roberts around?
Yes, she's around and she has messaged you. She says, thank you so much, Ashok. Lovely to be able to hear you talk today. I hope to be able to meet you again in person in near future. Best wishes from Aberystwyth.
Thank you so much. Share.
Yes,
I can't see them here. Okay, I don't have access to chat box here.
Oh, okay, no worries. I'm just reading out for you. So
okay, thank you so much.
So she said thank you, and also thank you so much, sir, for joining today. And we are hopeful to meet you soon in the ALD conference in India. And yes, and also invite you to some other technical webinar sometime, maybe where you can talk more about.
I will join. I will join.
Yes.
Thank you so much. I'm sorry about the mix-up, but something beyond me, and my students were helping me. So they have put their own laptop for me, and I'll see whether.
Yes, please convey my thanks to them where they have helped you out.
Okay, all the best. Bye bye. Bye bye.
Yes, thank you, everyone.